It's a great pleasure for me to be here. I'm Ratan. I work at IIIT Allahabad. So this is the campus of IIIT Allahabad. We have 3 departments: IT and EC and Applied Science, and I work in Applied Science, where we offer 2 biomedical engineering and bioinformatics courses. I'm in the biomedical engineering program, and apart from research, I teach medical imaging and real-time signal processing. Okay, today I will talk about the research work that we are pursuing for the last few years on photoacoustics. First, I will introduce fundamentals of photoacoustics, photoacoustic wave equation. Then we will talk about forward problems that we were involved to solve, and then experimental work that we have conducted, and inverse problem that we want to solve that we already solved, or we want to apply that. Okay, few words about photoacoustic research in India. Photoacoustics is a rapidly developing field. For example, for last few years, it has been the largest sub-conference in SPI BIOS, and it's a developing field. So there are many unsolved problems, and it's a new technology, and so it's easy to design research problems, and it is interesting from the point of view of basic science, and you can also develop technology using this technique. In India, photoacoustic works have been carried out at IISc and IIIT Trivandrum, IIIT Mohali, but as far as I know, but not greatly at IITs. Of course, Professor Swapna Banerjee and Vasudevan, they are involved in photoacoustic research. So it is an interdisciplinary field, so collaborations are required to really develop useful technology based on this photoacoustic technology. So I'm not a machine learning guy, rather I will talk about photoacoustic effect or photoacoustic signals that we can generate, we can produce from different biomedical systems, and photoacoustic imaging, tomography and microscopy. And I think some of you can use your machine learning techniques to extract some features from the signals that we gather. So it may be an application area for machine learning community. Okay, this is the photoacoustic effect. For example, you have an absorber here which is illuminated by a light, and it will produce acoustic waves. And this effect was discovered by Graham Bell in 1880. And what happens when you illuminate a tissue with light, it will quickly absorb the energy from the light, laser light, and it will undergo thermoelastic expansion very rapidly, and so it will produce a mechanical or pressure wave into the medium that you can detect using an ultrasonic transducer, and you can capture the signal, and then you can do many things. So you need an absorber here. So the typical parameters: laser source, we use 532 to 1064 nanometer, and it is 700 to 900 nanometer is known as optical window, where light penetration in our tissue is maximum. And pulse duration, we send laser pulses whose duration is about 5 to 10 nanosecond, and pulse repetition frequency is 10 Hertz. So every pulse is coming up with a frequency of 10 Hertz. So it's a slow imaging modality, it's not a real time. But Arun was talking about ultrasound imaging, which is a real time imaging modality. But this is restricted by this 10 Hertz pulse. Laser energy we generally use to 20 to 200 millijoule, and it depends upon the wavelength, so that that laser energy should not burn your tissue. And temperature rise, if you illuminate your tissue, we have seen that temperature rise can be on the order of millikelvin, and which will produce an acoustic signal so on the order of 1 kilopascal to 10 kilopascal, and the acoustic waves it will produce the frequency content will be from kilohertz to gigahertz. So it's a wide band frequency it emits. And many times people ask me that why do you use nanosecond laser to generate photoacoustic signals? Because, for example, light is now some light is coming and illuminating our tissue. So, according to this effect, still we are producing photoacoustic signals. Yes, in this process also our tissue is generating photoacoustic signals, but the problem is that we don't have SNR. SNR, signal to noise ratio, is not high. But when you use pulse laser to suddenly launch or illuminate a tissue within a very small time window, and then it will produce signals that is it will have much large signal to noise ratio. So it will be detectable and will be useful to for many groups. Okay, so the background is that your tissue will absorb light during this process. So tissue must contain some chromophores. Chromophores are the molecules, they absorb light. So if your tissue does not contain any chromophore, it will not absorb light and it will not produce acoustic signals upon optical illumination. So for example, hemoglobin, RBC, red blood cells, they contain hemoglobin, and our skin contains melanin. These are the known light absorbing molecules. So our blood or our skin or eyeball, they can produce photoacoustic signals. For example, so we can image blood vessels using this technique. We can study our skin properties using this technique. But these are known as hemoglobin and melanin are known as endogenous chromophores that are present within our body. For example, we want to visualize cancer cells, we will not be able to do that. In that case, you have to add some nanoparticles, external contrast agents, so that the cancerous cell will absorb light and produce acoustic signals. So these are known as contrast agents, and these are exogenous contrast agents. So you have to administer those things before the imaging session. So small part of physics. For example, if I illuminate our tissue by a light, so it will absorb the light and its temperature will rise. So the amount of temperature will rise will depend upon the thermal expansion coefficient, and this is the equation from class 12 physics books. And it will also create some pressure change, because the stress will develop, and this is the simple bulk modulus is defined in this way. You know my stress by strain with the negative sign, and so you can write dV by V equal to minus kappa is the compressibility, which is the reciprocal of this bulk modulus. Now consider a situation both these two things are happening simultaneously. So you can combine these two. The total volume change divided by the initial volume equal to this. And okay, now as we are using a nanosecond pulse, so it's a very fast process. We assume that that energy is deposited very instantaneously, and tissue did not have time to lose its temperature as well as the stress. So these things we impose, this is known as thermal confinement of thermal confinement and stress confinement. If you impose this, then you will see that tissue did not have time to expand. So you will put this thing dV by V equals to 0. If you do that, you will get pressure equal to beta T by kappa. So this is the estimate of initial pressure. So it will depend upon the properties of the, as he was telling, mechanical impedance, the property of a material. Here, how much energy will be developed within the tissue once we shine with the laser light. This is the amount, beta capital T by kappa. Okay, so small little calculations. This is the thermal confinement time. So your tissue, once we send some light to the tissue, it will retain the temperature. It will not lose. The diffusion will not will be active. So the thermal confinement time is given by this d squared by 4t, where d is the diffusivity of a tissue, and its value is for a soft tissue is 0.14 millimeters square per second, and stress confinement is defined by d by Vs. Vs is the velocity of sound. So if you put all these values, you will have an estimate that thermal confinement time is about millisecond, 18 millisecond, and stress confinement time is 67 nanoseconds. So that suggests us what should be the pulse width of a laser. So it should be less than 10 nanosecond if we assume we want to obtain a resolution of 100 micron. So this is the 100 micron. We have deposited light here, and for these 100 micron we are imposing this thermal confinement and stress confinement restrictions, and that will give you these are the, so this tells you what should be the pulse width of your laser light, and it will create it will produce 100 Pascal for 1 millikelvin rise of temperature. So the pressure amplitude it will generate, it will be 100 Pascal, and that is ultrasonically detectable. That's why we think that the signal it will generate, the photoacoustic effect would be able we would be able to catch that, record that, and we can use for to do many things. Okay, this is the photoacoustic microscopy setup developed by Linham Wang. Now he is at Caltech. So I will quickly tell you what is there. So you have two laser lights. They have focused that confocally to the tissue, and at the same time we have an ultrasonic detector, which is a focus transducer here. That focus is here. So you have your arrangement is such that the spot where light is coming, and you are catching the signal from that special spot. So you can make a raster scan to generate a 2D image. This is known as photoacoustic microscopy, and this is the image. You see that you can see that this is ultrasound image. This is the difference between diagnostic ultrasound that we generate and this is the photoacoustic image. You can see the optical contrast here, as well as the resolution is controlled by the transducer, this transducer. So that's why I will talk about that, what are the advantages of this technique. And this is the tomographic setup. That means you have a tissue here, and this is the ultrasound transducer, and light is coming from here, it illuminates the tissue, and your ultrasound transducer goes to different angular locations. It makes an angular scan and detects the signals at each angular locations, and then use reconstruction techniques to form an image. Okay, so advantages of PA imaging. What are the advantages of this technique? First of all, it will, in an ultrasound image, you are generating optical contrast. Number one, because the PA signals are generated by the absorbing regions. That means only the chromophores, they will produce the photoacoustic signals. The background signal will be very, very less because it will not produce acoustic signals. And therefore, it's better than ultrasound imaging. Next, we are using the power of ultrasound imaging as well in this work as well. For example, different optical modalities, the light cannot penetrate our tissue. It can go up to 1 millimeter. But here, the light is traveling in this one way. We are considering one-way traveling of light. So it will go and illuminate the object, and it will generate the acoustic signals, and it will be collected by the ultrasound transducer. So it's a one-way travel by the light. Another way, we are catching the ultrasound signals. We know that ultrasound waves scatters much less compared to the light waves. It is 2 to 3 orders of magnitude less. So we can image deep tissue regions using this technique. And it can provide both anatomical and functional information of the imaging region, because we are using light. So light absorption by the chromophores are different depending upon the state. So functional state, and from that we can so that may help you to study angiogenesis, cancerous tumor, how it is evolving with time, because that will give us not only anatomical but also functional information. Okay, so this is, with this background I will start what we have done in the last few years. So this is the photoacoustic wave equation. If you remember, he was showing a photoacoustic wave equation, that is the Helmholtz equation for ultrasound wave propagation. In this case, we have a similar equation. The only difference is we have a source term. On the right hand side, we don't have zero. We have a term which is known as source term. So it's slightly you need other techniques to solve this equation. And this is the standard wave equation, and this is the geometry. You have a source and light is coming, and your sound will be, this will release the sound waves that may be collected from any angular location. So this is the wave equation. We can solve this equation. This is the solution. This is a boundary value problem. You solve the wave equation inside the absorber and outside the absorber, and then you match those solutions at the boundary the way we solve this is a very common technique, and at the boundary we match pressure value as well as particle velocity, what he defined in the model. And if you do that, you will get this solution. You have sine q minus q cap cos q divided by q square. This is the Bessel's function, spherical Bessel function he defined in the modeling. So Bessel function is present here as well. So this is the solution, and these are the notations we have defined here. Okay. Basically, we are assumed we have a k to the power I k f r, and we have a r in the denominator. So you can think that it's a some constant into e to the power I k r by r. So some spherical wave with amplitude depending upon the properties of the tissue that or the region that we are probing. Basically, it's a spherical wave. Okay, this was available in the literature, and that was in this physical review letters paper. Diebold provided this equation, and he did studied theoretical as well as experimental signals. That was well known in the literature. But in our research, what we did actually we extended this work. Previously we had single particle solution, but if we have a multiple absorbers, what will be the solution? So we did this. Actually, for example, you have a blood, so you have lot of red blood cells. each red blood cell is an absorber. So if you have a collection of red blood cells, what will be the field produced by n number of cells? So that was the motivation for us, or that is the way we extended this work. And this is the that is simple. You have to linearly sum the signals generated by each cell. So we have an summation term that will be responsible for interference of acoustics waves generated by each cell. And this is the frequency domain solution, and if you take the Fourier transformation of this, you can generate the time domain signal. So this is the way you can mathematically calculate what is the time domain, what would be the time domain signal for a n number of cells. If you have only one cell, this summation will not appear. If you have n number of cells, this will appear, and then it takes care of interference of different waves generated by the individual cells. So that previously people assumed that, for example, blood is a homogeneous medium, and they do this thing, they analyze those signals, try to calculate blood oxygenation, attenuation of sound waves, optical wave intensity, etc. But in our approach, we actually assume it's a collection of particles. So for example, this may be valid. For example, in case of blood, we have cells. So we can go to the discrete description of our blood, and we can use the discrete particle approach to simulate the signal, PS signal. So this is the way we model blood or any tissue. Okay, forward problem. Forward problem that we have studied. For example, this is a blood. It's a 2D slide of blood. That means you have hematocrit is about 40%. You have many cells, non-overlapping circles. This is the normal when blood flows through our vessel. They are individual particles are corpuscles are flowing. But in some pathological cases, for example, for diabetic patients, your cells become sticky. They start to form aggregates. So we studied what will happen if you have a normal blood and you have an aggregated blood. So these things have been studied parallelly in ultrasound tissue characterization. So we found that this is for non-aggregated case. If you increase the hematocrit means the number of red blood cells you have within a blood volume. So if you increase that, your photoacoustic signal will rise linearly, and that we have found using experiment as well as our theory also shows the same trend. For aggregated cells, we have seen that if you increase a dextran, which is a chemical, if you add dextran in your blood, it will start to cluster your blood. It's a protein that promotes aggregation. And you will see as you increase the dextran concentration, your PA signal will increase, and after that it will decrease. That is a known trend found by different group. If your dextran concentration, if you increase, it will grow, and after that it will decline. That has been so the similar trend we have found, and we also compared our theoretical result, which is not shown here, but we know that theory as well as experiment, they show the same trend. Okay, so this is the blood effect of RBC organization. This is basically you are studying the effect of cellular organization on photoacoustic signal. In this case, we have studied effect of RBC oxygenation. Actually, in an RBC red blood cell, you have almost 280 million of hemoglobin molecules, and hemoglobin, they can actually absorb oxygen, and oxygen can bind with the hemoglobin molecule. For example, if it is not binding any oxygen molecule, that is known as the deoxygenated, and the hemoglobin molecule can bind up to 4 oxygen molecules. maybe 0, maybe 1, maybe 2, maybe 4. And if it is hemoglobin molecule is binding 4 oxygen molecules, this is known as oxygenated, fully oxygenated red blood cell. So we mix two things, or deoxygenated and oxygenated blood. Actually, people have done this experimentally. They have seen this is the experimental card, and we simulated those things. This is, for example, NO is the oxygenated blood. This is not blood, cells, and we have mixed ratio is 3:7. In this case, it is 8:2, and we have seen, or in this case, you define one parameter known as blood oxygenation, SO2, which is very important parameter. We often measure this thing. For example, in case of brain, how much oxygen is present in our blood in brain. That if oxygen declines, then our brain will not function in a proper manner. So in the ICU, you will see there is a oximeter in your earlobes or fingertip that continuously monitor our blood oxygen level. So photoacoustic people think that they can also develop a similar small instrument using photoacoustic method to monitor blood oxygenation. And we okay, and this is the optical absorption profile of oxygenated and deoxygenated hemoglobin molecule, and you see that in this wavelength and that wavelength the absorption are different. So if you have a blood that is a mixture of oxygenated and deoxygenated red blood cells, and if you illuminate light, your oxygenated blood RBC will absorb light in a different manner compared to the deoxygenated red blood cells, and they will produce different signals. And if you measure those collective signal and if you vary SO2 level, it will vary like this. Our theory showed that this is the way it will vary, slightly non-linear, and so experiment shows it will be linear. So this study did not exactly reproduce this trend. Then we extended we modeled our blood in a different manner. We thought, okay, we will not mix blood, rather we will gradually change the oxygen level, and we found that exact match between our simulation and the experiment. So this is the way actually if you know the photoacoustic signal strength at two different optical wavelengths, you should be able to estimate our blood oxygen level using this. Then we also studied photoacoustics of malaria infected red blood cells. Actually, what happens in malaria, the parasite goes into the cell, that goes inside the cell and start to eat the hemoglobin. So once it starts to eat the hemoglobin, it converts another compound known as hemojuin. And this is not good for sure, because we are losing hemoglobin that serves many things, many purposes. So if you plot this optical absorption extinction coefficient for hemoglobin oxygenated, deoxygenated and hemojuin, you will see this is the card for hemojuin and these are for hemoglobin molecules. And you see that if you probe here, your malarial infected cell will absorb light in a different manner. So it will produce different photoacoustic signals. With this assumption, this is designed and work that this is normal cell, this is slightly infected cell known as ring stage, this is tropozoite stage. Your hemoglobin has been digested by the parasite greatly, and this is the final stage known as season stage, where most of the hemoglobin RBC lost most of the hemoglobin. And okay, and if you study, we studied what will be the photoacoustic signal at for different samples at 700 nanometer. We found that it grows in this fashion as the disease progresses. So we yes.
Just very interesting research. So this is just taking the blood, right? If you have melanin, I know you didn't show the melanin absorption. So if you were to do this through the skin,
actually this is simulation.
Yeah, but just how much of this is dependent on
yeah.
So if you were to do this through the skin, non-invasively, then your melanin will also have absorption, which probably.
Yeah, that is the most challenge. There are two challenges because you have to overcome the tissue first, and then you will find malarial infected cells you will find one infected cells in a background of billion cells. So that's why I'm telling you, maybe the special, if we are capable to collect this signal and then we can employ special signal processing techniques, machine learning techniques to find out that there is a malaria cell. People are working because I have seen one group from University of Arkansas. They are very serious about it. They already developed some setup and they are visiting. They visited Africa. They are visiting India where malarial infection is high. They are trying to test their machine algorithm, etc. That is the main challenge. Actually, you have billions of cells, normal cells in the background, and you have only one infected cells. So I don't know whether practically it would be possible to isolate, or you may need significant dilution of your blood. Okay. And then, as I said, that with a cancerous cell, they don't absorb light because they don't have any chromophore inside them. So what people have done, they use some nanoparticles. For example, if you have a beaker and you have water and you have some cancerous cells, and then if you add 1 spoon of nanoparticles, and if you keep this thing for overnight, and in the morning you will say that all the nanoparticles are inside the cell. This is known as endocytosis, because cells, they don't like foreign particles outside in the environment. So this is the mechanism. They will eat and enclose in a particular region inside the cell. So this is natural. So if does, so your nanoparticles will automatically go inside the cell. And then if you shine your laser lights, the cancer cell will absorb light and produce signals. And this is, for example, this is a cancerous tumor here, and this is the background. This is the ultrasound image. You cannot see anything, but this is the photoacoustic signal. If you only highlight the photoacoustic signal, you can see this boundary, and if you can do a combined multimodal imaging, and you will see. And people have seen what is the effect of cell concentration and what or photoacoustic variation of photoacoustic signal as a function of cell concentration at different energy levels, and almost it is very linear. Actually, that motivated us to do some work in this direction. We also took some cancerous cells, and we added. This is a theoretical study. So we took some endocytous nanoparticle cells, and for nanoparticles, your light absorption varies in this way. You can see that this is known as Plasmon resonance, for which you will see a peak. That means your light absorption will be maximum at this wavelength for this size of nanoparticle. 10 nanometer, 25 nanometer, 40 nanometer. So you have a peak at 532, almost 532 nanometer. So if you illuminate your cancerous cells, which containing nanoparticles at 532 nanometer wavelength, the light, and that will certainly absorb a lot of amount of light and produce acoustic signals, and we will see that it will vary in this way. So we have shown that our model as well as the people, the results they have measured experimentally, they exhibit very close match. And another study, actually some people are trying to develop a setup known as photoacoustic flow cytometer. In case of light, we do that is available in different biology labs. They use light and they measure the angular distribution of light energy to estimate the cell morphology and size and shape, etc. People are also trying to do this thing using photoacoustics. For example, this is your blood vessel and you have a cancerous cell here. For example, in case of metastasis, you have a definite chance of observing a cell far away from the cancerous site. So this is the schematic. If you have a cancerous cell, and if you illuminate with light, that will produce slightly different photoacoustic signal compared to the normal red blood cells, and whether we would be able to collect this signal and do some signal processing, and we'll be able to tell, okay, there is a cancerous cell. And the power of this technique is that we should be able to overcome the barrier, skin barrier. We cannot use the fully optical modality to do that, because we want to also, advantage of ultrasound will play a crucial role here and enable us to detect that. This is the hypothesis. Okay, so we also did a study where we mixed melanoma cells with red blood cells and we generated signals. Then we do some spectral analysis of the signal, and you can see for a normal blood, this is the spectrum. For once you have a melanoma cell in your blood, your normal red blood cell, if you think it is as a sphere, it is about 2.87 micron. But cancerous cells is about 5 micron radius. So it's slightly large. So if you analyze the PA signal, you will get additional dip here before the dip that you will get for an RBC. So that may indicate that you have a cancerous cell here. And we also studied if you take a small, you have a RF line, you take a small region, you take the signal of a small region and do the histogram and feed with different Nakagami and Rayleigh or generalized gamma distribution functions, and we have seen how the fitting parameters vary with different cases. Actually, these statistical functions have been extensively used in ultrasound tissue characterization community. So we just employed those techniques to analyze our signals. Okay, experimental work. These are the simulation works. Although we blood work, we also did some experiment. Here we did some purely experimental work in Kolkata. For example, we have a tank. This is filled with water. We have a small cuvette with blood, and laser is going from here, and we have a ultrasound. In this case, it's a hydrophone that is placed behind the sample, and this is the signal. You can see some signals here. The motivation of the work was this is known as hemolysis. For example, we have a blood contains red blood cells, and red blood cells, they contain hemoglobin molecules. But in some cases, what happens, for example, in malaria infection, your RBC surface becomes ruptured, and what happens, your hemoglobin will be released in the blood plasma. That is not good for our health. So can we measure the amount of hemolytic blood present in the whole blood, that was the motivation. Actually, in our study, we always assume a discrete particle approach. That is, the chromophores are enclosed within a particular region. But in this case, we want to study if they are not enclosed, they are within the medium, what will be the difference in signal. So we prepared, this is a hemolytic signal sample, blood sample, where all the, we used 4000 RPM centrifuge, and then used some solution with less salt concentration, so that water goes into the cell, it starts to swell, and at last it will there will be an explosion, and therefore all the hemoglobin molecules will come out the blood serum. And this is normal blood, that is, cells are suspended in PBS, that is the saline water. And this is the microscopic image. You can see the cells here, you can't see the cells here. So this is the schematic of our measurement. This is the sample, and you can see that both the samples, they produce comparable signal at 532 nanometer, but at 1064 we have a different signal, and we try to explain our result using physics. And what we wanted to say that this technique may tell us, or it may be possible to quantify what is the amount of hemoglobin molecules, or 5 minutes. Okay. So this is and this is the, we did different energies. So these are the plots, and in 532 we don't see any difference, but at 1064 we have difference between the two samples. Okay, inverse problem. Actually, these are the whatever I have discussed up to now was the forward problems. That is, we know the system, we know the configurations, and we send light and we measure the signals. And the challenge is, if you know the signal and then try to estimate what are the properties of the tissue. That is the inverse problem actually. So we proposed a model framework to analyze the signals, and that will enable us to estimate the tissue properties. In this case, we will be able to actually mu, that is the absorption coefficient, and the average size. Actually, this is common in ultrasound tissue characterization. They estimate impedance mismatch, and they estimate this average scatter size. So I developed a similar framework for photoacoustics, studying the literature for a few years, and this is the wave equation, this is the solution. Then we defined a quantity known as the differential photoacoustic cross section, similar to the differential scattering cross section, and this is the form factors we defined, that is the differential photoacoustics cross section per unit volume in this way, and this is the main equation. You see that this depends upon the spatial organization of your nu. So you can decompose this thing into a coherent part and incoherent part, and we will use this incoherent part. This is similar to the ultrasound scattering method, and we will this is the correlation coefficient, and correlation coefficient can be written as in terms of covariance, and we will not use the coherent part. In ultrasound, actually this coherent part goes to 0 because your impedance is plus minus with respect to the background. In this case, it will not go to the 0 because mu is always at a positive value. So in ultrasound you can choose any part of the signal, but in this case we will only choose the central part of the signal. So the boundary signals are coherent signals, so we will not consider that. And if you assume that your correlation coefficient can be written in this fashion, that is known as fluid sphere correlation coefficient, you can use Gaussian correlation, you can use exponential correlation functions. These are already defined in the tissue characterization literature, and if you put that, you will get this, and you can define these your form factors. And then, for example, this is a signal, this is the boundary signal, we will not use that. This is the signal within this black box, we will analyze those. And then what will happen, we will take the spectrum of this signal, and this is the test sample. At the same time, we will need a calibration medium for which we will already collected the spectrum, and we will divide this thing, and we will optimize this equation. This is the test sample and this is the calibrated sample for which we know the size, and if we minimize this thing, it will give us an estimate of average size of our absorbers of the medium that we want to know, and then we will minimize this chi and we will get the mu, that is the standard deviation of your mu. And here we have simulated this. These are the spec. We took some agarose medium when we mixed, we placed some microparticles, 10 micrometer, 20, 30, 40, 50, and then we measured the PS signals. These are the spectra for those samples, and then we choose a bandwidth of this 100, almost 50 megahertz in this case, and we divided this served as a calibration spectrum, and these are the test spectra, and we divide and then fitted with those functions, and these are the, after optimization we found this fits, and we can see this is the results that your nominal values are this, and this is the bandwidth, and estimated values are this, mu variance and size have been estimated in this way, and this for different functions. But this is simulation, it will not be easy in practice because now I will take 1 minute, right? Okay, I will finish now. Okay, over here. So some people in China and in collaboration with the University of Michigan, they are also doing similar studies, and they found they use spherical correlation function to estimate the size of the absorbers. And we think we should be able to do some experiment. We will employ this method and characterize different blood stage, for example, blood aggregation, effect of oxygenation using this. And if you take a, for example, malaria cell is present in a blood, so what will be this blood with a malaria cell and without a malaria cell. So maybe these parameters may give some, will give some light to find out the presence of cell. Okay, I'm done. Thank you. In the next talk, we will talk more about PS signals analysis and imaging. This is more or less for solve forward problems, design or develop methods to address inverse problems, and we are also currently doing imaging, tomography and microscopy, that we will talk tomorrow. Okay, thank you for your patience.